Good afternoon, everybody. Hopefully you're having as good a weather as we are here in sunny Minneapolis today. Um, again, my name is Gary Maxon. I'm the engineering manager, filtration engineering manager at Caloris Engineering, and we're going to be talking about RO condensate polishers. And actually, we're probably going to talk a little bit more than just condensate. There's other various feed water sources that we'll be talking about. And those sources for our RO polisher, they can be typically what we'd be getting into is reclaimed water. They could be evaporator condensate from milk and food products. They could be reverse osmosis RO permeate from milk and food product concentrates. They could actually be from wastewater, and they could even be a mix of city water too. I mean, it could be a mix of all these. And the reason we're talking about city water is, you know, at times, you know, the city water might be a filler when the reclaimed water does not fully meet the demand. The plant might need so much water a day, and if the reclaim doesn't fill that up, we take city water and clean up the totally dissolved solids out of that. City water, just so you know, that could be from a well water source, or it could be from a surface water source, local lake, a river, or whatever. Okay, a little bit more about reclaimed water. The one we're mostly getting into is evaporator condensate. Everybody should be aware that that's typically going to have low total dissolved solids. It is going to have some organics, and they definitely play a role in the design of the RO. And you need to know if carryover could be a concern, you know, with a poorly designed evaporator or whatever. Carryover is a concern. You definitely got to look at the design and, you know, how you design that polisher. With evaporator condensate, because you have low TDS, you can typically design that with high recovery. So that recovery is the feed permeate ratio, and with evaporator condensate, we can usually get 90% recovery. The next water source would be RO permeate. That's probably going to have high TDS. It's going to have organics in it. Going to have, if you have RO leaks, then you're going to have a plant for suspended solids, and you can figure you're going to get pretty high recovery on that. The reason you have high TDS is, you know, the ash content, many of these RO permeates is very high. So even with high rejection membranes, we could easily get the 200 above for the TDS, where, you know, the evaporator condensate, you're probably going to be below 50 most of the time. And then the next source could be wastewater. You're always going to have organics. You know, unless you do good pre-filtration, you can have suspended solids, and you know, the TDS could be all over the map. It depends on what the wastewater is and how good your pre-filtration is. City water, pretty good water. The only issue with that is it's going to, if you're getting it from well water, you're going to have high DS. You need to plan for that in your RO. It's going to have probably low or no organics, which is a good thing. Hardness is your biggest concern, and because of the hardness in the water, you're only going to get a recovery of 60–80%, so it's a low recovery. And then if the source is from surface water, probably going to have low TDS, but you're going to have organics, which you need to plan for. And then you're probably going to have low hardness. Okay, RO polisher design. There's three main designs. There's the array type, that's low cross flow. There's the array with recirculation. That's going to be a mid-range for cross flow, and then recirculation stages. That's going to be, you know, the same design as a lot of the food and dairy type plants with a lot of suspended solids uses, and it's going to be designed with high cross flow. So this is the array type, and just really simplified. You're going to have a feed pump. You're going to have that feed pump would feed into stage 1, the concentrate from stage 1 would feed stage 2, and the concentrate from stage 2 would feed the last stage, and you collect the permeate on all the stages. That would go to your permeate silo, and then the concentrate all the last stage would typically go to drain or wherever you're sending it. So by far the most common industry and the cheapest is this array type. Array type with recirculation. In this design, it's the same as the array type, but to get a little bit more cross flow, we'll take a split stream of that concentrate and actually run it ahead of the feed pump. So a little bit about cross flow rates. The previous example, the array type, you know, you could get as low as 15 GPM per 8-inch membrane, which is fine for good water, but for water with organics or any kind of issues with it, suspended solids, 15 GPM is just way too low. You're not going to be able to clean it up. But the array type with recirculation, there you're probably going to, you know, get cross flows rates in the range of 30 to 40 GPM per 8-inch membrane. And then the final type of polisher would be with recirculation stages. Now this is typically used in applications with high suspended solids and tough cleaning requirements. And here you're going to get into cross flow rates of, you know, 80 to, you know, as much as 100 GPM per 8-inch membrane. Okay, so which design to use depending on your water? You know, a lot of people just you know, say, well, I'm going to use recirculation stages for everything, and you know, that's, you know, if you don't mind paying the extra money, that's you know, going to be a workhorse design, and you know, it'll take care of you if you have high organics, if you have some evaporator carryover, if you have possibility of membrane leaks, and you have high cleaning requirements. It's just a good design, fairly simple design, and you know, it's going to work for most feed water sources. The next one would be for array stages with recirculation. This you would use if you have some organics, you know, enough organics to create cleaning issues. You just need a little extra oomph for cleaning. And then you have none of the other issues that are in the recirculation stage design. And the only time you would use the array stages design would be as if you're using some pretty clean water and all you're dealing with is some you know, high TDS and some hardness, you know. And you know, this typical design is you know, you probably clean it every 1 to 2 months, and that's it. You know, there's just no cleaning issues, and you know, runs great as long as the water's great. Okay, the next part I'm going to be talking about is what if you want to create potable water from reclaimed water? So now this particular this is from the latest dairy PMO, and it's actually the only water standard I'm aware of that it goes from reclaimed water to a potable water standard. And I am aware that other industries use this, or at least they start from this standard, but I'm not aware of any standards in other industries. So to meet this requirement, you need to not exceed a total plate count of 500 per milliliter. Following commissioning, you need to collect samples daily for the first 2 weeks, meet the standard, semi-annually thereafter. And this is provided daily tests are conducted for 1 week following any repairs or system alterations. So say you have a UV light for disinfection and you need to repair a light or replace a light, you need to collect these samples for a week again and pass all the tests. You need to be below a standard turbidity of 5 NTU, and then, or the electroconductivity could be less than 12 milligrams per liter. I think most systems I'm aware of just go off that turbidity standard. You need to include fail-safe monitoring devices, example, divert valves. So if you exceed the standard, you have divert valves downstream that will divert it to drain. You also need to have satisfactory organoleptic quality and no off flavors, odors, or slime formation. And this needs to be sampled and tested weekly. Approved chemicals such as chlorine and or urine disinfection may be used to suppress bacterial growth. And to be honest with you, you need something like this to keep it below the 500 plate count per milliliter. Water reclaimed from raw milk shall be heat treated at times and temperatures provided by the PMO. So that means somewhere in the process that milk needed to be heat treated with a legal pasteurizer. Okay, so and then one other requirement, if you're recovering any of the heat, so this is a big requirement for water reclaimed from milk and milk products used for heat exchange in a raw milk heat exchanger. So a lot of requirements here. See, the raw milk side of the heat exchanger shall always be under lower pressure than the water side. The reclaimed water between outlet from the heat exchanger and the nearest point downstream shall rise 12 inches above any raw milk or milk product in the system. The heat transfer water circuit shall be full of water and automatically replenished whenever raw milk or milk product is present in the heat exchanger. All raw milk or milk products shall drain freely back to the upstream supply tank when pumps are shut down and when the raw milk or milk product line is disconnected. And any pump located between the raw milk or milk product inlet to the heat exchanger and balance tank shall operate only when water is flowing through the heat transfer section and the pressure is at least 1 psi greater than the pressure of the raw milk or milk product. So basically what that's saying is, it's preventing raw unpasteurized milk from leaking to the water side. Okay, disinfection methods. The three big ones would be UV light, HTST or heat treatment, and chemical additions such as chlorine or any other disinfectant source. So UV disinfection, this is rapid, effective inactivation of microorganisms through a physical process. When bacteria, viruses, and protozoa are exposed to the germicidal wavelengths of UV light, they are rendered incapable of reproducing and infecting. UV manufacturers must comply with a strict PMO guidelines in the dairy industry. And they're pretty strict because I've seen UV lights that meet the PMO standards. There's going to be typically 5 times or more the cost of a non-PMO UV. And then one other note about UV disinfection, which I'll talk a little bit more on the next slide, is you got to understand it's short-term disinfection only. So, well, anyway, I'll get into it on the next slide. Okay, so the next one is HCST disinfection. This just means a legal pasteurizer similar to raw milk pasteurizer. Typically, substantial cost increase from UV. So the only reason you would use a pasteurizer is if you don't have, if you just have raw milk is what you're recovering the reclaimed water from. So somewhere in the process you need to actually go through the legal pasteurizer. So if you don't have it in the process anywhere, then you need to do it on this. You need to do it in the final disinfection process. And what I was saying, this is also short-term disinfection. So at the outlet of that pasteurizer, everything's going to be dead, but it has organics in the product. So any bugs that get downstream, they're going to be concerned. You're going to start growing. So that's what I mean by short-term disinfection only, and you need to, design it so you can take care of that issue. Okay, oxidant addition, by far the lowest capital cost. It does have long-term disinfection. But the problems with chlorine is, a lot of plants don't want chlorine in their plants. An issue is if you use free chlorine for CIP and you're using it for a CIP on an RO system, you need to neutralize that chlorine before you use it, or you'll quickly destroy your RO membranes. And then one thing is, you got to worry about possible NDMA formation. NDMA is a carcinogen. Outside the municipal industry, not too many people probably understand what that is, but it's a big problem in municipal water plants that chlorinate waters with organics. So municipalities have spent loads of money trying to take care of that problem. And if you're using this reclaimed water, you could have the same issue, or you should at least be aware of it. Okay, how do we design for pre and post storage of the tanks for the polisher? So, like I've been talking about, we need to really look at the organics closely in this water. If we have organics in the water, they're going to quickly lead to microbiological growth downstream, and you'll even have same growth upstream too. So the recommended design is shown here is to have dual tanks feeding the polisher and dual tanks for your Cat 1 potable water. And these should be cleaned every other day, because if you don't clean them, you go more than a day or two, you're definitely going to get pretty good bio-growth film on the outside of your tanks. And that if you use that for CIP water, then all those bugs are going to get throughout your plant and cause issues. Okay, last slide. This is what are the uses for Class 1 potable water? Probably the biggest use I'm aware of is CIP water for cleaning your equipment, including the final rinse. be used for boiler feed water. It could be used for culinary steam. Can be used for product displacement water at the end of a run. Can even be used for product water, filtration, brine, etc. The only issues is, again, you gotta be aware there's going to be could be trace organics, and they could be a quality concern. You know, getting into your product, you know, whatever. And if that is a concern, you don't want that in your product, then I'd suggest, and you don't want the high TDS in your product from regular city water, then I'd suggest using well water for your RO source, and that'll give you the best quality water. And with that, I'll take any questions at this time.
Okay, Gary, I don't see any questions yet, but we'll give folks a couple minutes to use the Q&A feature if they would like to. And in the meantime, I do want to remind folks that we have another webinar scheduled for next week. Actually, Gary, if you wouldn't mind stopping your screen share, I'll bring up those details again.
Okay, thank you, everybody.
So next week's webinar will be on improving evaporator efficiency, and the speaker will be Bruce Skinner, our sales manager. You can register for that by visiting the link caloris.com/caloris-webinars. And again, that is where you can find the upcoming schedule for webinars, as well as links to our past recordings. And in about 24 hours, that's where the recording for today's webinar will live. We do have one question, Gary, and that is, would you normally recommend city water or evaporator condensate for high purity RO water?
I would recommend, if you want high purity, I would recommend cleaning up city water with an RO.
Okay. If you want to be among the first to know about our upcoming webinars, I would encourage you to join our mailing list if you haven't already, and you can do that by scrolling to the bottom of any page on our website and entering your email address where prompted. We only send out one email a week. It's an e-newsletter that includes relevant industry topics, resources for plant managers, and announcements like our webinar series. So that's all we send out. If there are questions that you didn't want to answer in the webinar setting, you can send email to info@caloris.com. That goes directly to me, and then I will forward your question on to the appropriate person. And we are also actively seeking suggestions for future webinar topics. We do intend to continue offering this webinar series throughout the summer. So we want to hear from you as to what burning questions you have that we can help answer. So again, you can either enter that in the chat feature here or send me an email. Again, that's info@caloris.com. I don't see any more questions, so I am going to go ahead and close up the webinar for today. Thank you, everybody, for joining us, and we hope you enjoy the rest of your week and will join us on a future webinar.
Thank you, Missy.
Thank you.